In this video, we are going to discuss about example of complex exponential orthogonal function. And this is the example of complex exponential orthogonal function. The example is prove that complex exponential signal are orthogonal function. Coming to the solution, so given that we have to consider two complex exponential functions, two complex exponential signals that are first signal is x of t is e power jn omega naught t and second signal is y of t is equal to e power jm omega naught t, where small m and small n are the integer. Now we have to consider the interval t naught to t naught plus capital T, where capital T is the fundamental time period. The fundamental time period capital T is equal to 2 pi by omega naught. The fundamental time period capital T is equal to 2 pi by omega or 2 pi by omega naught. So the condition for if the two complex exponential signals are orthogonal to each other, that is the condition is integral t naught to t naught plus capital T x of t y conjugate of t dt is equal to 0. So this is the condition for orthogonality condition in complex function. If this condition is satisfied, as the given two signals are complex exponential signals are orthogonal, otherwise it is said to be non-orthogonal complex functions. So now we have to consider the LHS term, that is integral t naught to t naught plus capital T x of t y conjugate of t dt. And now substitute given two signals. The given two complex exponential signals are x of t is e power jn omega naught t and y of t e power j m omega naught t and y conjugate of t. So y conjugate of t is the complex conjugate of signal y of t. So the y conjugate of t is e power minus jm omega naught t. So these two exponential terms can be written as e power a into e power b is e power a plus b. So e power jn omega naught t into e power minus jm omega naught t is written as e power j of e power j omega naught t minus m omega naught t. In the power of exponential, both the terms take the common j omega naught t. So e power j n minus m omega naught t dt. So integrating this RHS term, e power ax integration is e power ax by a. So e power j n minus m omega naught t by j into n minus m omega naught over the interval t naught to t naught plus capital T. And now substitute the upper value of small t and lower value of small t. The upper value of small t is t naught plus capital T and lower value of small t is t naught. So that is e power j n minus m omega naught into upper value of small t is t naught plus capital T minus e power j n minus m omega naught into lower value of small t is t naught divided by denominator term j into n minus m omega naught. So now here on RHS side in the first term, numerator of the first term, multiplying this omega naught within the bracket term. So we have omega naught t naught plus omega naught t and e power so e power a plus b is e power a into e power b. So now here, so e power j n minus m into omega naught t naught plus omega naught plus capital T is written as e power j n minus m omega naught t naught into e power j n minus m omega naught capital T. And the second term is as it is same, divided by denominator. In the numerator term, here both the terms take the common. E power j n minus m omega naught t naught is common. So that is the RHS term can be written as e power j n minus m omega naught t naught divided by j n minus m omega naught into e power j n minus m omega naught capital T minus 1. So we know that the fundamental time period capital T is equal to 2 pi by omega naught. So omega naught into capital T is 2 pi. So that is the RHS term is e power j n minus m omega naught t naught divided by j into n minus m omega naught. Here omega naught into capital T is 2 pi e power j n minus m 2 pi minus 1, where small m and small n are the integers, and substitute different integer values of m and n. Different integer values of m and n, the term e power j n minus m 2 pi is 1. So therefore, the RHS term is e power j n minus m omega naught t naught divided by j into n minus m omega naught. Different integer values of n and m. So this exponential term is 1. So 1 minus 1, 0. 0 into something, 0. So the RHS term is 0. So therefore, integral t naught to t naught plus capital T x of t y conjugate of dt is equal to 0. So the orthogonality condition is satisfied as the two given complex exponential signals are orthogonal to each other. Thank you.